One of the important topics in your book in this chapter is on how computers represent data. I'm on slide 14 in the presentation, and this is where it starts to explain this a bit. You know that your computer is an electronic device and therefore has two possible states. It has an on state, it has an off state, and it uses a digital signal to represent data. The digital signal is represented, again, a 0 represents off, a 1 represents on. So every character on your keyboard is represented by a series of zeros and ones. This is called the binary system. And so binary, bi meaning two, there are two possible numbers. The numbers are a 0, again, for off, and a 1 for on. So just as an example, a character on your keyboard, let's say, for example, the letter H. If you're looking at the letter H, it's represented by 8 binary digits, 8 bits, if you will. So right here. Those 8 bits are 8 zeros and ones. So every character is a series of 8. So imagine, if you will, a Word document or a computer program, and how many characters you have, how many zeros and ones it would take to write out something like that. And that is exactly how data passes through your system. So a few things you should know. So a bit is a binary digit, as I was saying. A byte is 8 of those, and a character takes up 1 byte or 8 bits. Second part of this is understanding how to convert binary numbers to decimal numbers or decimal numbers to binary numbers. So if you look at the following slide, I have a breakdown of an example. So in my example, remember that the binary system is a base 2 system. When we say base 2 because there's two possible values, 0 or 1. The decimal system is what we know, and that's considered a base 10 system because there's 10 possible values. We have 0 through 9. So now take a look at these examples side by side. So I'm going to give you a number in decimal, 1,210, and a number in binary, 1010. And if I ask you to take this number in binary and convert it to a decimal number, the process you would go through is to understand what the value is for each of these positions, multiply it by the value, and then add them together. So take a look at my chart for the decimal number 1,210. Right, here's the place value. So the place value is 10 to the 0 power, 10 to the first, second, third, etc. You see the pattern. Then if you expand what the value is, 10 to the 0, any number to the 0 power is always 1, then a 10, then 100, then 1,000. Now take this value and multiply it by what you have here. So that's a 0, a 10, 200, and 1,000. Add them all together and you get your decimal number. So to convert a binary number, it's a similar pattern. The place value is 2 to a power for each of these, right? Because you can have only two possible values. So 2 to the 0, 2 to the first, 2 to the second, 2 to the third. Now this is a 4-binary number, a 4-bit number rather. If I asked you to do an 8-bit number, you would just continue the place value pattern. Then it's expanding the value. So you know that 2 to the 0 is 1, 2, 4, 8, etc. Now, what's the value at each position? So you have a 0 here. Here you have a 2 times 1, which is 2. A 0 again in this place value. And 8 times 1, which is 8. Now add your 8 and 2 together, and you get 10. So the binary number 1010 is the same as 10 in decimal. And if you take a look at this example here, I have a slightly different example here, 1001. You go through the same process again, right? And that's a 9 in decimal.